Welcome to The Explainer. Today, we're diving into one of the most incredible, almost mind-bending technological mysteries of our entire lifetime. We hear the term artificial intelligence thrown around absolutely everywhere these days, right? But beneath all those flashy buzzwords, there's a fascinating, surprisingly elegant mathematical engine running the show. Today, we are going to explore the actual beating heart of modern AI, the artificial neural network. Seriously, just take a second and look around you. Your phone can unlock instantly just by recognizing your face. A streaming app somehow knows exactly the kind of weird, obscure movie you want to watch tonight. Software can literally listen to you speak and turn it into text in real time. And the craziest part? These aren't just parlor tricks. Nobody sat down and programmed every single rule for these systems. They actually learned to do these things. Which brings us to our big hook for today. How does a machine learn that this picture is a cat, predict what you'll watch next, or understand your voice? Okay, let's dive into this, because that right there is the central mystery we are going to solve. How can a bunch of numbers learn? I mean, really, how does math learn? To help us wrap our heads around this, we're going to use a single, really relatable analogy throughout this entire explainer. I want you to think of a neural network like a dedicated student, okay? A student who is studying for a massive, wildly complex final exam. They're going to take thousands of practice tests, and they're going to learn entirely from their mistakes. Now, right off the bat, let's clear up a massive misconception. An artificial neural network is not a literal, biological simulation of a human brain. There's no consciousness here. It doesn't think like you or I do. What it actually is an incredibly advanced statistical engine. Instead of relying on a human programmer to write rigid, line-by-line code for every possible scenario, which is impossible, by the way, it acts as a dynamic system. It just fits complex mathematical curves to massive piles of data so it can recognize patterns. At the very heart of this system is the artificial neuron. This is the fundamental, tiny little mathematical processor. So, if our whole network is the student studying for the big exam, you can think of the artificial neuron as a single brain cell trying to process just a tiny, microscopic piece of study material. It receives some information, processes it, and then decides, hey, is this important enough to pass along, or should I just ignore? Let's break down the anatomy of how that actually works. First, we have the inputs. This is just the raw data coming in, like the actual text of the practice test question our student is reading. Next, we have weights, and weights are absolutely crucial. They represent how much importance the neuron gives to that specific input. In our student analogy, it's like the student deciding, how much do I actually trust this specific flashcard to help me pass? Then we add what's called a bias. This is basically a baseline adjustment. Think of it as the student's natural confidence level before they even read the question. Finally, we take that total score and push it through an activation function. This is a mathematical twist. You might hear terms like ReLO or sigmoid, but basically it warps the number. And without getting bogged down in the math, just know that without this nonlinear twist, the network could only ever draw straight lines. And the real world, it's way too messy and complex for just straight lines. Now, what's really interesting about this slide is how we transition into part one of our process, the test, or in technical terms, forward propagation. You see, a single neuron by itself isn't going to get much done, so they get organized into layers. And the flow of information here is strictly a one-way street. First, the raw data enters the input layer. Our student sits down and reads the test question. Then that information flows through one or more hidden layers. This is where the magic starts. The network is extracting deeper, more abstract patterns. The student is processing the concepts, linking all these ideas together in their head. Finally, the information hits the output layer, which generates the final prediction. The student picks up their pencil and writes down their absolute best guess. But what happens if that guess is wrong? Say the network confidently predicted the answer was 30, but the actual correct answer was 100. We measure that gap using something called a loss function. Think of loss as the giant circle of red ink the teacher puts on the student's practice test. The loss is the exact error margin. It tells our network, mathematically, exactly how spectacularly wrong its prediction was compared to the real answer. Which brings us to part two, the correction. This covers backpropagation and gradient descent. Here's the thing. Getting the answer wrong isn't a failure in machine learning. It is literally the entire point of the exercise. The real magic doesn't happen when making the guess, it happens right after. And this introduces one of the most important concepts in all of modern computer science, backpropagation. When our student gets that test back covered in red ink, they don't just toss it in the trash. No, they work backward. They look at their wrong answer and trace it backward through their whole thought process. Which exact flashcard totally misled me here? Which textbook concept did I rely on way too heavily? Backpropagation is an incredibly efficient algorithm that figures out precisely how much every single weight and bias in the entire network contributed to that mistake. And all of that together gives us our fundamental learning loop. Step 1, predict. Use forward propagation to make a best guess. Step 2, measure the error. Calculate that loss to see how painfully wrong the guess was. Step 3, adjust. Armed with the knowledge from backpropagation, the network uses an optimization trick called gradient descent to physically update those weights. Actually, scratch that. It's more like tuning the little knobs inside the network. Our student is actively adjusting their study habits. They're deciding to trust that misleading flashcard a little less and trust a better textbook a little more, ensuring that the next time they take a practice test, the loss will be just a tiny bit lower. And this brilliantly illustrates what happens over thousands or even millions of cycles. The network continuously, mathematically shifts its internal numbers. The weight given to those trusted, highly accurate inputs goes up. The weight given to the misleading, noisy inputs goes down. The student's accuracy steadily improves, not by some kind of digital magic, but through relentless, microscopic tweaks to these numbers until the whole system becomes mind-blowingly precise. All right, moving to part 3, the final exam, inference and overfitting. So AI actually lives in 2 completely different phases. Everything we just talked about, that grueling, intense loop of guessing, calculating loss, and tweaking weights, that is called training. And it requires huge amounts of time and computing power. But once training is finally over, we enter inference. This is it, the final exam. The network's weights are now completely locked in. It stops adjusting, and instead, it rapidly fires off predictions on brand new, real-world data it has never ever seen before. When you ask a chatbot a question on your phone and it answers instantly, you're experiencing inference. But there's a huge pitfall here. It's called overfitting. Imagine our student studies for the practice tests by literally just memorizing the answer key. Oh, question 4 is always C, right? They score a perfect 100% on the practice runs, but then they sit down for the actual final exam. The wording of the questions is slightly different, and they totally bomb it, like complete failure. They just memorized the raw data. They never actually understood the underlying concepts. Data scientists spent a huge amount of time trying to prevent neural networks from doing exactly this, making sure they can actually generalize to new data in the real world. Which leads us to part 4, the foundation of modern AI. Okay, so once you truly grasp that foundational loop of forward and backward propagation, we can scale it way, way up to see how these massive systems are changing the world today. You've probably heard the buzzword deep learning, right? Sounds super sci-fi and intimidating, but honestly, it literally just refers to the depth of the network. A shallow network might only have 1 or 2 hidden layers, great for simple tasks. But a deep neural network stacks dozens, sometimes hundreds of hidden layers together. And that depth is everything. It allows the network to build wildly complex, abstract concepts. The very first layers might just spot edges in a photo, but the middle layers combine those edges into shapes, and the deepest layers combine those shapes to say, hey, that's a human face. And from that core, deep architecture, we've developed some incredibly powerful, specialized descendants. We've got convolutional neural networks, or CNNs, which are totally specialized for analyzing images. We have recurrent neural networks, RNNs, which have a kind of memory and are great at tracking sequences over time. And of course, we have transformers. This is the heavy-hitting architecture powering today's massive large language models, like the chatbots taking the world by storm. But here's the best part. As crazy specialized as they are, every single one of them still relies on that fundamental loop we just talked about. Guess, measure, adjust. So why does all of this actually matter to us? Well, because these elegant mathematical loops cascade into the tools we rely on literally every single day. We're talking face and fingerprint recognition. We're talking systems that can scan a medical image and spot a disease faster and sometimes more accurately than a human doctor. Speech transcription, predicting the weather, and generative AI that can write code or answer incredibly complex questions in seconds. The whole shebang all stems from a bunch of numbers learning to just minimize their own error. So the crucial point is, and if you remember absolutely nothing else from this explainer, remember this. A neural network doesn't magically know the answer. It learns patterns by repeatedly making predictions, measuring its mistakes, and adjusting its internal parameters. That relentless loop of trial, error, and adjustment is the true engine driving artificial intelligence. And those simple ideas are the foundation beneath much of the AI we use today. But honestly, it kind of leaves you wondering, doesn't it? If these networks can learn to see, speak, and even reason just by mathematically adjusting their numbers, what on earth will they learn to do next? Thanks so much for joining me on this explainer, and we'll see you next time.